So hello friends, welcome back. In last video we built a TDS water quality monitor and we have also used LCD, right? And now today we are adding a turbidity sensor to measure the suspended particles. So in this video I'm going to show you how we can add another sensor on another ADC pin. Our setup will remain same, but this time we will measure another quality, or you can say another parameter to measure the cleanness or the measure the quality of the water, which is the cloudiness, right? So this part we have already covered, and this is what the turbidity sensor is look like. This left side you can see the sensor, and right side it's our setup. So in last video we have added up to this TDS sensor, but now in today's video I'm also going to explain you how to interface this sensor with the circuit and how to measure the water's cloudiness, or you can say measure the suspended particles in water, dirt, right? It's like how much water is cloudy, right? If for the clean water, it shows the clean, or you can say high ADC, or in another way you can say low NTU. NTU is a measurement how you can measure the quality of the water, right? And for dirty water, it will be high. So the relationship is inward. So before understanding this, what is turbidity means. So first let's understand what turbidity is. So while TDS measures dissolved solids in water, turbidity measures suspended particles like things like dirt, algae, and sediment that makes water cloudy. Right now, turbidity measure in this NTU. It's a parameter called nephelometric turbidity unit. Right now, for clean water, the value should be between 0 to 5 or very, very small. For swimming pool water, it should be 0.5 to 1. Right? For river water, it should be 10 to 100. And for very muddy water, it would be 1000 plus. Right? So these are standard thing. However, today we are just trying to implement the thing. So this criteria may not meet, but we will try our best to achieve the experimental thing, right? Which we can demonstrate and which we can understand. This is what our main goal is. So the principle of the sensor is like it has two different you can say input. One is a transmitter. They are not input, but you can say like a probe. So transmitter transmit the signal and receiver will receive the signal. Here left side you can see if the water is clean, then whatever transmitter will transmit, same signal will receive by the receiver. So here you can say with zero loss, or you can say nearly near zero loss. So in this case you will have high, what we can say, a output, right? So receiver will receive maximum thing whatever transmitter transmits. But in case of dirt or in case of particles, this scenario will change. So as water is dirty, as much as number of particles are increased, the signal will distorted and the receiver will receive very, very less, you can say, signals, amount of signal. And hence the ADC or the output voltage will be very less. So it's like an inward type of thing. For clean water, output voltage will be high. For dirty water, output voltage will be low. Okay, so let us understand this as a graph, you can say. So let us assume this is ADC, and we have 12-bit ADC and all. If you don't know, then please watch my previous video. So ADC, so as voltage increase, this ADC also increase, right? But from this concept, if ADC is high, the water is clean, right? And if ADC is low, the water is dirty. So you can say this is the cleanest water, right? And this is the dirtiest water. I can write like that. Okay, so this will be our overall thing, right? You can draw it as like this. So ultimately you have to measure the ADC. If ADC is high, water will be more clean. If ADC is low, water will be bad, right? So this is what the overall principle. And our sensor connection are like sensor is having 5 volts, so simply are connected plus 5 and ground, and one output pin is connected with PA4. So here you can see in this diagram also our PA4 is around this wire is PA4, right? This one. So this is PA4, and other things is ground and plus 5 volts. So because we need two plus 5 volt, one for this LCD and one for the sensor, so I've used breadboard in this video, right? So this is what the overall connections, right? And main important thing is this conversion, right? So you have to remember this thing. Now let us open our code, right? So this is the same code which I've explained you in last video. Now here I added only one thing, right? And which is info. I just enable one more pin of ADC 1, and this pin is around here, PA4, you can see, right? And then I just generated the code. So now in this code we have PA4 also available. So I have to simply program this PA4, and other thing will remain as it is. So for that, again you can see we have all the functions which I already explained you, right? ADC and this, how to read this TDS sensor, right? Other ADC parameter. Now I'm just adding one more function. It's a float read, and this time I'm going to read turbidity sensor, right? So this function will read the turbidity value. It will convert the value into required number, and then we will display that number on our LCD. So let us take one float parameter. Now let us configure ADC, right? So to configure the ADC, we have to write some configuration parameter, and because we are using this channel number 4, so I'm just using some configuration parameter which I have already pre-written over here. So I'm just taking them as it is. These are the configuration parameter, right? So what we are telling this microcontroller, that I'm going to use channel number 4 at ADC. Okay, this is sampling cycle and this is configuration channel. So I'm just telling that my ADC is ADC 1 and my channel is channel number 4. That's it. Now rest of the thing is same as we did in our TDS part. So I'm just taking 30 samples. Sample is again a variable, so you can take any value. In our current example, it is 30, so it will take 30 samples continuously and then average it, and that is how we will get stable value. Okay, and now let us start the ADC. So this thing is also I already discussed. The function to start the ADC is HL ADC start, and here you have to write the handler, right? Handler of that ADC. So our ADC is H ADC 1. So this will start our ADC. Now we have to wait until it will convert the final output. So for that we have poll for conversion, right? And here again we have two argument. One is the handler and one is a timeout. And we have to wait until it become HAL OK. So HAL OK indicates now our conversion is done and now we can read the value. Okay, so it will take very small time, but we have to wait for this. And now we have to store our value into some variable, and to get the value we have this function HAL ADC get value. Again here also we have to pass the handler. But now we have to save this somewhere, right? So for that we have this variable ADC samples I, right? And this is already we have declared over here, right? Number of samples. So this is the variable where we will store 30 different values, continuous 30 different values. And then let us find the sum. So it will continuously add this one by one. Okay, and finally you will have total sum of all ADC. Now once we have totals of 30, let us stop this. And to stop, again we have to write HAL ADC stop, pass the handler, and wait for some delay or wait for some time. Let us put 30. It's small number, right? So now we have the final sum of 30 value. Now we have to find the average. So ADC average will be float. Here I'm typecasting the final answer. We have this ADC sum divided by samples. Okay, so this is very simple. We are simply finding the average. So sum of all 30 divided by 30 will give us average, right? Now this is the main important part. So this is the calibration part. So as I told you earlier, for clean water, let us say ADC clean is some number, right? This could be any number. I'm just taking it 2800. This is ADC rating for clean water. And as I told you earlier, for clean water, ADC will be high, right? But at the same time, our output NTU should be low, as low as possible. So ideally, let us take it as a 0, right? And same way, let us add one more calibration point, but this time for the turbide water, right? $300. You can change this, you can calibrate this, right? But in this lecture, on this video, I'm just going to explain the concept. Later on, we will calibrate this and make final product which can use to measure the quality of water. But this time I will just explain you the concept. Okay, so for clean water the NTU would be high, so let us take this as 1000, right? So here I have two different calibration point. Okay, and now we will write equation for slope like NTU is equal to mx plus b. X will be your ADC value, right? And we'll calculate the slope. Float m is equal to Now let us try use this formula. Turbid water minus clean water, okay, divide by turbid ADC minus, sorry, clean ADC. Okay. So we are calculating the slope. Now we will calculate the intercept. We put y, sorry, b will be the slope, right? Now we will use NTU clean minus slope into ADC clean. So this is our intercept. And now we will apply this in equation. So MTU will be M into ADC plus B, right? So our final turbidity would be, we have slope into, we have ADC average plus B. I will explain you this calculation in more detail in another video, because this video will become more and more longer. So that's why I just uh, stick with the concept. Okay, not, we are not going in much in mathematical calculations, but this is what the turbidity calculation is. And now let us limit this, because we have to make sure this limit will not cross certain value. So if turbidity is less than 0, we will keep turbidity is equal to 0. And same way, if turbidity greater than 3000, let us stop it or keep it 3000, not more than this. Because if your calibration goes wrong, you will get infinite value, right? Which is not perfect. So just keep this in mind. Whatever calibration value you will define, ultimately you have to limit this, okay? Because in ideal instrument, it should be within the range. It is not like infinite thing, right? So now this is the calibration. It uses y is equal to mx plus b. We measure ADC at two known NTU values. Okay, because we know this ADC two known calculated value, we calculate the slope and intercept and then apply the formula. Okay, main part. Now again, we have to call this function in our main program. So where is our main program? Yes, this is the main code. Let us store this value somewhere. Turbidity value is equal to this, right? I have to declare this actually. So let us declare this with TDS value. So now we have this turbidity value. And now we have to convert this. So this is TDS value into 0.5, right? F. So we have to write similar thing for our turbidity value as well. So I'm just taking another integer. We typecast this final calculation into integer. Let us write this turbidity value plus F. Okay. So this is also I added it. Now change UART output to include this turbidity. So here we have this UART buffer, right? And here I'm just adding, I'm just removing this totally and just keeping this TDS as it is. Percentage B ppm turbidity, percentage D NTU. This is the unit. And I'm just passing only two things. One is TDS and one is turbidity, right? It's turbidity. So this is what the UART part. Now update the LCD as well. So in LCD we have this first line, we have measured this TD, we have displayed this TDS, but now instead of this, let us measure the TDS. Okay, so we will keep this TDS on first line only. Now we will display the turbidity at the end of the second line. Okay, so for that we have C9. So as I told you earlier, this C0 means second line, C9 means second line, ninth column. So this turbidity part will start from the line number, column number 9. Okay, so let us take character and just use this function as it is. Line 2, this time we are using line 2, and this, instead of TDS, it should be TUR, right? Remove this ppm. We are not going to write anything because we have limited space, and this variable should be int, right? And we will simply add this on the LCD. So we will simply write LCD string send string line 2. So this is the line 2. So on first line we have TDS, then on second line, column number 9 will be turbidity is equal to the value, right? And now let us add water assessment. So on C0, on line number second line in first column, okay, now simply put condition. If our TDS int is greater than 900, means if our TDS value is greater than 900, and if our turbidity value is greater than or equal to 300, we have to simply write. Let us use this formula as it is. We are not going to copy anything on any value. Just write bad. So water is bad. Okay. Now, if else if TDS value is greater or equal 600, and if the turbidity value is around 150, sorry, yes, we have to change this part, right? Around 150, let us write fair. FAIR. Copy this again. If this value is greater than 300, and if this is greater than 50, we can say, let us write it's good. Else, and if the TDS value is less than 300 and turbidity value is less than 50, let us write excellent, or simply XEXE, excellent, right? And now this is the end of the code. Now I'm just releasing this target. Let us check for possible error. Now here some error is there in this ADC average. Okay, this should be ADC average, right? This is just typing mistake. Now let us check for another error. Samples, I think it should be samples, right? So these are just typing mistake because I'm holding this device from one hand. Now let us upload the code. Meanwhile, let me show you the circuit. Now you can see these are the connections. So I have just used clean water. Now let us upload the code. So this sensor is placed over here. This is the TDS sensor. This is the turbidity sensor. Now code is uploading. And now you can see the output. On LCD, you can see TDS and this turbidity. It is showing good water, right? Now let me add this dirty water over here. Let me simply change the sensor from here to here. TDS sensor from here to here. Let us observe this. It is showing fair, right? Now this is dirty water. So let me just slowly use this spoon to make it more and more dirty. And now you can see this value is increased. So this is how you can add another sensor. So this demo is actually measuring the TDS value as well as the water, how cloudy the water is. So this is what for today's video. In next part, I will add another sensor, and then we will make a complete project. We will use SD card and create a data logger where we will simply record the sensors value continuously. So this is what for today's video. If you like my work, then please like my YouTube videos, subscribe the channel, share it with your friends. Till then, bye bye. Thanks a lot.